Okay, in this lesson we are going to talk about polar coordinates, and it's something that has kind of been hiding in plain sight, and we just haven't given it a name. So I'm going to show you an example of what I mean. So we have been talking about trig functions, and we've drawn lots of pictures like these where we can use this type of picture to define all of the trig functions. So sine of theta is y over r, cosine of theta is x over r, tangent of theta is y over x, and so on and so forth. And what this section, and this picture here, we're using the Cartesian coordinate plane, right? So if we look at this picture, we have the Cartesian coordinate plane. All right, it's this thing that has the x-axis, which is a copy of the real number line, and the y-axis, which is another copy of the real number line. And we can use this Cartesian coordinate plane to describe any point in the plane, right? We use an x-coordinate and a y-coordinate, and now we know exactly where any point in the entire plane is. It's also called the rectangular. It's also called the rectangular coordinate plane because, right, every point here creates some sort of a. You can think of this point as creating a rectangle using the origin and the y-intercept and the x-intercept, or the x value and the y value that correspond to that point. But the thing that we can also do is we can describe this point in a different way. So let's call this point P, point Pxy. We can also describe this point using just r and theta. And by describe, I mean locate. Oops, lowercase r. And by locate, I mean, right, so if I told you to graph, if I said, hey, graph -2, 7, we would all be able to, we would all graph the same point. We could all locate that point in the Cartesian coordinate plane, and we would all get to the exact same point. And what we can do here is we can actually use r and theta to also describe this point. So we can also describe this point using r and theta. And if we describe this point using r and theta, we would all find the exact same point, as long as we know that we're talking about this different coordinate system. And I think this might be easier if we look at a couple of examples. All right, so there's this new coordinate system called the polar coordinate system. These are polar coordinate systems, and it lives, right? It lives kind of on top of the Cartesian coordinate system, or the Cartesian coordinate plane, right? And here I have two different versions, right? One version has radians and one version has degrees. Again, they both live in the same place. We're just writing it a little bit differently. And let me just show you how to find a few points. So let's find the point P1, comma, pi over 4. Let's actually do that in red. The point 1, comma, pi over 4. So remember, the 1 is the r, and the pi over 4 is the theta. Now, how do we find this point? Okay, we find this point by first going to, well, there are a few ways to do it. Let's call this, let's call that radius 1 and that radius 2. Okay, so first we go to this polar axis here, and we find 1, so we find our radius 1. So that means that we are somewhere, that 1 means that we have to be somewhere on this circle with radius 1. Now precisely where are we on that circle with radius 1? That's where the angle comes in, and the angle says, oh, we're precisely at pi over 4 radians. Okay, so again, this angle here, that's our theta. So this is the point 1 comma pi over 4. Another way we could think about this 1 pi over 4 is we could, instead of first going to the radius, we could first go to the angle pi over 4, right? So we could have first said, all right, we're at this, you know, we're somewhere on this line, somewhere on that line. Where are we on that line? Well, since the 1 is positive, and we'll talk about this more in a minute, since the 1 is positive, it means we move towards the pi over 4 angle. All right, so let's try one with degrees, and let's do a negative 1, 120 degrees. And let's call, just to make this a little bit easier, let's assume that this is the circle with radius 1. All right, so now 2 ways to figure out where this point is. We can first start with the r value. Remember, this is r and theta. Okay, since the r is negative, though, we would come over here first. If the r was positive 1, we would go over here. But since the r is negative, we come here, and then we go 120 degrees. So 180 plus 120 is 300. So we would end up right there. So this is the point Q, negative 1, 120 degrees. Or, right, since we think about the angle first, right, we think about the angle, so we know that we're on this 120 degree line somewhere, so we go to this angle, and then since the r is negative, right, if the r was positive, we would go up here, but since the r is negative, we go the opposite way, and we end up going down there. Okay, let's do point R, and let's do both of them negatives. So let's do negative 2 comma negative 4 pi over 3. So 2 ways to do this, right? We can first think about the r, and then we can think about the theta, or first we can think about the theta, and then we can think about the r. Okay, so since the r is negative 2, so negative 2 or positive 2, we know we're going to be on the circle of radius 2 somewhere. Got to be somewhere on the circle of radius 2. So if we think about the r first, the r being negative says we go over to here. Okay, so first we would go over to here, and then we go negative 4 pi over 3. And then the negative angles and positive angles are just like normal, where positive means we're going counterclockwise and negative means we're going clockwise. So we're here and we go clockwise 4 pi over 3. Okay, and 4 pi over 3 is going to wrap us all the way around. Right? So here's 3 pi over 3 brings us all the way here, and then another pi over 3 is going to bring us right here. So this is r, negative 2, negative 4 pi over 3. Or we could think of the angle first. So negative 4 pi over 3, right? Where's negative 4 pi over 3? Negative 4 pi over 3 brings us all the way to here. So this is the, so 2 pi over 3 and negative 4 pi over 3 are coterminal, right? So we know we're on the, somewhere on the negative 4 pi over 3 line. And then since it's, if it was positive 2, we would end up here. Since it's negative 2, we end down here. Okay, and let's do one where, let's see, which one haven't we done? First one positive, so let's do 2, and the second one negative, negative 150 degrees. Again, we have R and we have theta. Let's see, where's 2 going to be? So this is 1, 2, 3, 4. 1, 2, 3. Oh, shoot. Well, right, we don't have enough. 2, 3, 4, 1, 2. Yeah, we don't have enough room, so it's gonna. We're gonna be somewhere on this next outer ring. I'll try to draw it. Sure, we're gonna be somewhere like out here. Next ring out. Okay, if we do, so if we do the R value first, right, we go to positive 2 and then negative 150. So then we have to think about like coterminal angles, which positive angle is the same as is coterminal with negative 150, and that's 210. So here's the point S, 2 comma negative 150 degrees. Okay, or we can do the negative 150 first and say, okay, we're on this, hold on, I gotta focus. We know we're somewhere on this negative 150 line, okay, and here's the positive direction, and then this would be the negative direction. And just a little bit of vocabulary. This right here, right, the middle, this is called the origin or the pole. So we call this the origin, which is the same name that we have for the Cartesian coordinate system, or the pole. And then the polar axis is just, if we're thinking about this using in the Cartesian coordinate sense, it's the x-axis, but only the positive part. Only the positive part. Now, maybe you've noticed this already, but one thing that is different about the polar coordinate system and the Cartesian coordinate system is there's more than one way to describe these points. In fact, there are infinitely many ways. So I'm going to describe the point P in another way. Right, I'm going to describe the point P in another way. We did 1 comma pi over 4. We also could have used, what if we used negative 1 instead? If we used negative 1, then our angle would have been 5 pi over 4. And I knew when I drew this line it was kind of screwy. It should have been, sorry, here's that. There's that pi over 4 line, right? Negative 1, 5 pi over 4 gets you to the exact same spot. Okay, or we could have used a negative angle, right? We could have used negative 7 pi over 4. So P can also be described as positive 1 and then negative 7 pi over 4. Negative 1, or positive 1, negative 7 pi over 4. And even another way is we could have used, let's see, negative 1, negative 3 pi over 4. Right? Negative 3 pi over 4 is going to bring us to this line, and then negative 1 is going to bring us back up there. So there are, and we could, okay, I'll do one more. Okay, we could have done, let's do positive 1, and then let's do see, 9 pi over 4, right? Because the 9 pi over 4 is going to wrap, right? Here's 8 pi over 4 is one complete revolution, and then another pi over 4 is going to bring us to 9 pi over 4. Another thing we can do that is sometimes useful is let's try to convert p, which is 1 pi over 4, to Cartesian or rectangular coordinates, right? What if we wanted to use x's and y's to describe that point? Right? What if we wanted to use x's and y's to describe the point 1 pi over 4? So let's graph it on the Cartesian coordinate plane. X, y, 1 pi over 4. Okay, this is pi over 4. And r is equal to 1. And now the question is, what are x and y? What are x and y? Now this is a familiar triangle. Okay, remember, this is the 45, 45, 90 triangle. 1, 1, square root of 2. So this triangle here that we drew is similar to this triangle, which means all the ratios to the sides are similar. So what we can do if we want to force this hypotenuse to be length 1 is we can just divide everything by the square root of 2. So if we divide all sides by square root of 2, we get 1 over root 2, 1 over root 2. So now here we know that y is 1 over root 2 and x is also 1 over root 2. So our Cartesian coordinate point is 1 over root 2, comma 1 over root 2. So we've successfully converted from polar coordinates to rectangular coordinates. And now I'm going to talk about how we can do that much more. Well, there are lots of relationships that make this a little bit easier to do. So let's talk about those relationships. We're going to start out with our pretty standard picture. X, Y, R. Right, we've drawn this picture 100 times. And this point P, we can think of it as a rectangular point, or we can think about it as a polar point, right? So this is what I mean by the fact that the Cartesian coordinate plane, right, where this is the x-axis and this is the y-axis, and the polar coordinate plane, where we're thinking of this r as the radius of some circle, right? Both of these coordinate systems are living in the same place simultaneously. So this r-axis is also, we can also think about the positive portion as the polar axis. And now we can come up with a bunch of relationships between x and y and r and theta, and we actually know all these relationships already. Okay, so we know that sine of theta is y over r. So if we solve this for y, we know that y is r sine of theta. So if we know r and theta, then we can just automatically figure out y by plugging those in. We know cosine of theta is x over r, so x is r cosine theta. Okay. We know tangent of theta, right? This is nothing new, is y over x. And we know that x squared plus y squared equals r squared. So when we were looking at our point 1 comma pi over 4, right, when this was r and theta, if we wanted to figure out the corresponding y coordinate, right? Y is r sine of theta, which is, in this particular case, is going to be 1 times sine of pi over 4, which is 1 times 1 over root 2, which is just 1 over root 2. And similarly, our x is r cosine theta, which is 1 times cosine of pi over 4, which is 1 times 1 over root 2, which is just 1 over root 2. So we also could have found the Cartesian coordinate, the corresponding Cartesian coordinates, by using these relationships, right? We found them before, right? Remember up here, we figured it out by knowing this this triangle. But we can also use these equations. All right, let's do a couple more examples here. All right, so let's find the rectangular coordinates for the point that has polar coordinates 4 pi over 3, or sorry, 2 pi over 3. So our r is 4, and our theta is 2 pi over 3. Now we can use what we just figured out. So y is r sine of theta, and x is r cosine of theta. Okay. In order to do this, I would have to graph my my 2 pi over 3. So there's my 2 pi over 3. R is equal to 4, so that means that this is pi over 3. Actually, yeah, let's do it without the. Let's just use our standard triangle, right? This is a 30, 60, 90 triangle, right? So we know that y is square root of 3, x is -1, and r is 2. So now if I want the sine of 2 pi over 3, it's y over r, which is root 3 over 2. If I want the cosine of 2 pi over 3, it's x over r, which is -1 over 2. So now if I want to find my corresponding components, I have 4, which is my r value. Right, that's my r value, times sine of 2 pi over 3, that's my theta value, and we just figured out that sine of 2 pi over 3 is root 3 over 2, so we get 2 root 3 as our y-coordinate. For cosine, we have 4 times -1/2, which is -2. So our corresponding Cartesian point is -2, 2 root 3. All right. So we had to use our 30, 60, 90 triangle and reference triangles to figure out sine of 2 pi over 3 and cosine of 2 pi over 3. Another way we can do this, which is similar but a little bit different, is we find this point for 2 pi over 3 on the on our polar coordinate system, right? So 2 pi over 3 is going to be right here. So that's going to be 4, 2 pi over 3. And then we can kind of imagine that we have our Cartesian coordinate system here as well. Right? So again, we're simultaneously thinking of this as the polar axis and the x-axis. So we know r is 4, and we know this is 2 pi over 3, so our reference angle is pi over 3. Now, how do we figure out our x value and our y value when our r value isn't standard, right? Because our standard, well, here's our standard right here, actually. We already drew it. Right? Here's our standard 30, 60, 90 triangle over here. So r is 4, here r is 2. So how do we what do we have to do to this side? How do we scale this r equals 2 to get r equals 4? And the answer is we just multiply it by 2. So if we multiply every single side by 2, right, then we get our x and y coordinates. Oops. So y is 2 root 3. So again, right, we get the same answer. It's just a little bit different way of thinking about it. Now we're going to go the other way, right? We went from polar to Cartesian. Can we go from Cartesian to polar? And we'll do it kind of two ways. We'll just do it in the purely algebraic way, and then we'll do it maybe a little bit more geometrically. So remember, x squared plus y squared equals r squared. So we know x and y. So we have 4 plus 4 equals r squared. So r is plus or minus the square root of 8. And then we'll have to figure out which one exactly. And then we know, right, now we have these other relationships. We know sine of theta is y over r. Cosine of theta is x over r. Tangent of theta is y over x. Since we're not quite sure if r is positive or negative yet, right, I think we should use the tangent of theta because we know precisely what x and y are. So we know tangent of theta is negative 2 over 2, which is negative 1. Okay, now which theta value gives us negative 1? There are two of them. We can use the arctangent. Certainly, we can use arctangent to get theta equals arctangent of negative 1, and that's going to give us negative pi over 4. But we would also know, right, that arctangent only gives us solutions in the fourth and the first quadrant. So we'd have to think that, oh, we could also use theta equals 3 pi over 4. That's another angle that gives us a tangent of negative 1. Okay. And now we just have to decide, like, what combination of r and theta is going to give us the right thing. And if we think about this point is going to be in the fourth quadrant. So we can see that, okay, the negative pi over 4 is going to bring us down to the fourth quadrant, and then we would, if we're going to stay in the fourth quadrant, we want the r to be positive. So root 8 comma negative pi over 4 is going to work. Or negative root 8 comma 3 pi over 4 is also going to work. And there are infinitely many other solutions as well. More geometrically, right? If we want to do this more geometrically, we can plot the point. Y is negative 2, x is positive 2, and then we can use our XYR definition. Sorry, we can use this relationship, which we know exists, this x squared plus y squared equals r squared, and always think of our r as positive. So we get r as positive root 8. And then we notice that, you know, this is a 45, 45, 90 because these two sides are the same. And we know that that this angle here is going to have to be negative pi over 4. So that's another way to figure out the root 8 negative pi over 4. Because we have these relationships between polar coordinates and Cartesian coordinates, we can also convert polar equations to Cartesian equations and vice versa. So, for example, right, we want to convert x squared plus y squared equals 9 into a polar equation. Now, the reason we would want to do this is sometimes polar equations are kind of more easier to understand. Like when you look at x squared plus y squared equals 9, there's a lot going on there. It's not a function, right? So if you graph this, it's not going to pass the vertical line test. And you're squaring the x's and they're squaring the y's, and it's a little bit complicated. So how could we convert this to a polar equation? And then once we do, I would argue that the polar equation is easier to understand. So again, recall that x equals r cosine theta. Again, just coming from our xyr definition. And y equals r sine of theta. So let's substitute those into our equation, and we get r cosine of theta squared plus r sine of theta squared equals 9. So we have r squared times cosine squared of theta plus r squared sine squared of theta equals 9. And then we can factor out an r squared. And cosine squared plus sine squared is 1. So r squared is 9. So r equals plus or minus 3. This is our polar equation, right? And they're actually both the same. Now what does this mean? This means, so this is, okay, so what points are these? These are all points on polar coordinate plane with r equals 3. And these are all points on polar plane with r equals -3. Those are the same set of points, right? It's just a circle of radius 3. And maybe you noticed that x squared plus y squared equals 9 is also a circle with radius 3. And I would argue that these are a little bit simpler to understand. R equals 3, radius equals 3, distance from the origin equals 3. That describes a circle. So if I look at this, r equals 3, and I look at x squared plus y squared equals 9, to me it's a lot easier to recognize that the r equals 3 is a circle. All right, let's go the other way. All right, let's start with a polar equation and convert it into a rectangular equation. So let's convert r equals 2 cosecant of theta into a rectangular equation. So, right, if you ask me what does this look like, now this is very complicated. R equals 2 cosecant of theta, I have no idea. Okay, so now the goal is to get rid of the r's and thetas and see what we can come up with. So, let's see, I think the first thing, I don't like to think about cosecant, so I'm going to think about that as 1 over sine. And then, let's see, I'm going to multiply both sides by sine to get that out of the denominator, just so I can think about that a little bit easier. So r sine of theta equals 2. But then, remember, right, y equals r sine of theta. So this is y equals 2. And this, right, which is very, to me, that's very easy to understand. That's the, right, here's the x-axis. And here's y equals 2. So again, this equation, y equals 2, in Cartesian, the Cartesian equation in this case is a lot easier to understand than the polar equation, which is the opposite of what we had in that previous example. Let's do one more. And this is more of a, this one's a little bit different. We're going to try to figure out what the graph looks like. So what does the graph theta equal, let's do pi over 4. look like? Okay. Right, because we knew that, right, when r was constant, so like r is 4, this is a circle of radius 4. Circle of radius 4. So it's all points 4 comma theta, right, where theta has no restrictions. Theta is between negative infinity and infinity. Any angle, right, which creates a circle. So now we're doing a different one where now we have, this is just kind of an aside, sorry. Now we have theta is fixed. So this is all points r comma pi over 4, where r is any value. So r is between negative infinity and infinity. Now what do these look like? Right, well, pi over 4, again, we're thinking about polar. This is the polar axis. So here's our pi over 4 angle. And then what is r? R can be anything, which means that we actually just fill in these dots. So theta equals pi over 4 is a straight line at the angle pi over 4. So if we want to, I didn't ask this, but if we wanted to convert this to Cartesian, right? This is the graph of y equals x. All right, theta equals pi over 4 is the same as y equals x.